Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is carding theory. So, during carding we know that we have discussed that fibers are transferred from one surface to another surface through pins on the different cylinder surface, on Likarin surface, even in the flat surface the pins are there, and also finally in the doffer surface. So, this transfer from the fiber from one surface to another surface, that is actually that these are followed by different theories. So, here we will discuss some theories and how different zones act on this theory, follow these theories. So, carding classical theory that we have already mentioned in our last session. So, carding action is purely by mechanical means. So, that is the action of carding is by mechanical means, although for fiber shading from the surface, like from doffer surface, there is a air current also comes into picture, but it is as far as carding action is concerned, it is a purely by mechanical means, by a pair of pinned surface, and they are oriented, they are inclined in different direction. So, this we have already discussed here, and what we found that cot alpha is more than mu. Mu is the friction, coefficient of friction between fiber and the pin surface. Okay. So, it does not consider the centrifugal force, air current and the air drag force. So, carding action here in the during derivation of this equation, what we have only considered the mechanical means, that is the force acting on the fiber and the coefficient of friction. But in addition to this, during carding, due to the rotational motion, centrifugal force act on the fiber, which tries to throw the fiber out from the surface, and air current, air drag is also there, air current, air vortex created. So, this all also affect the carding action. Now, point to point configuration here for carding. Here we have already discussed this part. So, P2, this force P2, and R is the force on fiber, and P2 is the force, downward force, which is actually which tries to hold the fiber to with the cylinder pin. This is cylinder and this is the flat cylinder pin. So, this is trying to actually hold back the fiber, fiber tries to stick to this surface for force P2, and P1 is the force P1 sin theta, it tries to pull the fibers out of the of this surface, and where and the for effective carding action the fiber should stay with the wear point. Okay. And this P1 force, this P1 force here, it is if you this normal force, and mu is the frictional force, it also helps in the to stick to the fiber, okay, to the wear surface. These two forces are there, but R always the pulling force by the flat always tries to take the fiber out from this. surface. So, P 2 is more than mu P 1, if P 2 is more than mu P 1. So, the wear point where we will try to actually take the fiber along with it, which keep the fiber along with it. So, it will stay with the wear point. Okay. And so, r cos alpha is more than mu r cos alpha. So, we get cot alpha more than mu, that we have already discussed in last session. And here we have already mentioned that cotton, for cotton it is less than 74 degree, and for wool it is less than 77 degree. It is a typical value of this. Okay. Now, along with this, which we have not yet discussed earlier, the parameters, factors which we have not discussed, these factors are centrifugal force, air current and air drag force. These three force we will discuss here, and how are these forces affect this carding action. Okay. Now, if you see the, as per the Strang's theory, which is based on Prandtl boundary layer theory, what does it say? A series of concentric air layer. So, this is a cylinder. Okay. Now, concentric air layer will be there, series of concentric air layers are there, because it is actually shearing. Because when the cylinder rotates, this is the cylinder, when it rotates, the concentric air layer will have some movement surrounding this cylinder. Okay. So, a series of concentric air layer infinitesimal thickness surrounding the cylinder and rotate with its different velocity. So, there will be relative velocity will be there. So, when cylinder rotates, the different layer above the cylinder surface. So, this concentric surface, they will have the velocity. So, cylinder velocity is linear velocity is V c. So, the layer which is actually close to the cylinder, which is which is in touch with the cylinder, it also rotates the at the cylinder velocity. So, this is this rotates, and as the distance from the cylinder increases, the air velocity reduces accordingly. At certain distance, the velocity becomes 0. Okay. So, that is the system here, and here it is a flat is there. So, which is, and in between the fibers are there. So, these fibers are, in addition to the wear pin inclined wears, that wear points. So, in addition to that, fibers are also getting affected by the that air drag. Okay. The movement of air drag. So, the tufts are opened by the shearing action of air. So, that is, there is a shearing force also acting. So, tufts are opened by the, mainly opened by the wear point. In addition to that, there is a shearing force. Why is it why there is shearing force? Because in the, suppose there is a tuft here. Okay. At this portion close to cylinder, the air velocity is very high, and here the air velocity is very low. Suppose it is a air velocity, it is 0. at this. So, there will be a shearing action acting on the fiber surface, fiber tuft. So, that helps in opening also in addition to the wear points. So, this shearing force, so we must know the how much shearing force is there. So, according to the theory, the shearing force is F is equal to R V A by D. What is R? R is the coefficient of viscosity of air layer at a particular temperature. So, viscosity of air also changes like a liquid with the temperature. So, at a particular temperature, the coefficient of viscosity is given by R. V is the velocity of air current. So, at that point, what is the velocity of air current? And A is the projected area of fiber tuft in the direction perpendicular to the air stream. Now, this A is important, like one tuft is this is there, okay, this is the tuft. Now, and perpendicular to the air. So, if it is the air movement, okay, air stream direction, and the perpendicular area, this is the area of perpendicular area, that area projected area is the area, that is the A projected area. Now, instead of this, suppose we have another fiber, so which is projected in this fiber, in this type. Here you will see the projected area will be different. Projected area will be different. So, shearing force will be different. So, higher projected area means higher shearing force. Okay. So, here you will see the projected area will be much less. So, lower projected area will have lower shear force. So, that if the fibers are directly facing the air stream, that will have higher shear force, and the D is the depth of air boundary layer. So, what is the depth of air boundary layer? The higher the depth, so that means higher depth of air boundary layer will be, that is the distance from this cylinder surface, in this present case cylinder surface. So, as the distance increases, the force will be less. So, it is inversely proportional to the distance. Kaufman's theory, it says that, so here we can see these are the pins, wear points, okay. This is the cylinder wear points, and flat is normally in a pin surface. Now, these are moving in the same direction, but cylinder moves at a very high speed. So, there will be carding action. So, compressive force will be there when the cylinder is a flat and cylinder, their distance are very small, maybe 0.3, 0.4 mm that distance, and the fiber tufts, the fiber tufts are much larger than that size. So, what happened here? So, there will be compressive force acting on the fiber tuft, and when cylinder moves at a higher speed than flat. So, let us see, this is the say flat and fiber due to the compressive force. So, these are the pins. This is flat surface and this is the pin, okay. And you need, suppose fiber, this is the fiber tuft. So, fiber tuft cannot penetrate easily. So, it needs compressive force. So, cylinder, when cylinder comes here, cylinder has got pins. So, due to the presence of both the surfaces, the cylinder surface and flat surface, this is compressive material, fiber tuft is a compressive material. Due to this compressive material, these fibers penetrate inside the pins of both cylinder and the flat. Okay. And here what happens, suppose this is a flat, these are the cylinder pins from the top view of the surface. This is the cylinder flat pin and here is the cylinder pin. Okay. Now, with this pin, suppose fibers are arranged in this fashion. Okay. Within this, it is penetrated in this from the in the tuft form. Now, if they are moving in the some there is a relative motion, this fibers will be actually moving through these pins and get straightened, get segregated. So, fibers from there, if there is any cluster formation, suppose let us see there is a cluster formation, this is one fiber and here is another fiber. So, two fibers are forming cluster, and when they move through this wear point at different velocity, this cluster formation will be removed. So, that is the basic function, so that fibers will get individual identity. Okay, here. Now, the carding action is finished by the time tuft passes to the 5th or 6th flat. So, there are flats, there are a series of flats, this is a cylinder, let me draw, suppose this is a Likarin cylinder doffer and this is the flat surface. So, flat has there are series of 40 to 50 flats are there. So, this is the type of flat moves in this direction, cylinder also moves in this direction. So, flat. So, first flat, this is the flat 1, flat 2, flat 3, flat 4, flat 5, 5th, 6th. Okay. So, flat 6 like this. So, this process, this opening process continues, the tuft moves through this different flat segments. So, it enters from this zone, okay, and by the time it reaches to 5th or 6th flat, it fibers gets actually carding action is completed. So, after that only the fibers are carried by the cylinder, okay, and short fibers are carried by the flat. So, that is a system. The compressive force developed in the flat and the subsequent friction field are responsible for carding action. So, this compressing force is developed by the flat and that helps in carding action. Without compressing force or without friction field, the carding action will not be, it is not possible, okay, because there has to be some friction field and also that is due to the compressive force. So, this is the Kaufman's theory. Now, we will try to see the carding force, what are the parameters on which the carding force depends. First is the Likarin speed. So, higher the Likarin speed, lower is the carding force up to the 15th flat position. So, why? The higher Likarin speed means the fibers get opened. So, what is the carding force? Now, carding force is the force what is carding force? During this movement through the cylinder surface and flat surface, it needs a force to actually open up the fiber. So, the force that which is required during this action, it is called carding force. Okay. So, the Likering, the higher the Likering speed, that means the fibers are already opened. If the fibers are in cluster form, the entangled form, the carding force will be high. But when the fibers are relatively open, so that means the during the carding the force required will be less. So, the lower carding force up to the 15th flat position. So, that means it reduces, after that carding force is very low. So, that means that from 16th onward the carding force does not depend on the Likering, because Likering speed is actually affect the carding force at the initial flat section. Thickness of operational layer. So, thicker the layer, the higher is the carding force. Obviously, that means this is the flat, here is the cylinder. That means, if the fibers are more number of fibers are there, but thicker the fibers, thicker the operational layer means more number of fibers, that means it require higher force. So, for thicker layer its higher force is required, that means more number of fibers are there. So, which will require higher force. Now, cylinder speed. So, higher cylinder speed results in thicker operational layer and higher centrifugal force. So, that is also important. Centrifugal force is also important, as I have mentioned. So, higher cylinder speed result, the operational layer will be thicker, because the ultimately the transfer will be to the doffer will be same, but the transfer coefficient will be reduced because of the higher cylinder speed. So, the operational layer will be thicker. So, it will give higher carding force and also higher centrifugal force due to higher rotational speed. So, it results higher cylinder speed increases the carding force. So, that is due to the two factors. One is the operational layer gets thicker and it increases the centrifugal force. That means, the fibers are actually there will be higher compressive force on the flat due to the higher centrifugal force also. That means, higher cylinder speed results higher carding force. Cylinder flat setting, because as I have mentioned, this is a flat and here is a cylinder. If we have same material, now this is one case, another case is closer setting. Setting is closer and same material is there, that means closer setting will result higher compressive force. Higher compressive force on the tuft and closer setting increases the carding force. So, setting, if we increase this reduce the setting, so carding force will increase. Fiber type. So, coarser fiber with higher flexural rigidity will increase the carding force. That means, if the flexural rigidity is high, it will resist the movement of the, it will resist against the fiber tearing off due to higher flexural rigidity. So, for coarser fiber the carding force will be high because its rigidity is high, but in case of fine fiber, as they are very flexible, they take care of, they actually follow the path of the curve of the this curvature of the wear point, which is created by the wear point, that will actually absorb the force little bit. Okay. Sixth is the fiber friction. So, fiber to fiber friction is very important here. So, higher fiber to fiber friction means it will fiber to fiber, even fiber to metal friction. So, because we have already seen that actually by the from the theory that carding is a function of sliding past the fibers to fiber sliding and also fiber to pin. So, fiber to pin sliding, that is the carding basically. One fiber will move at higher speed, another will be moving at lower speed. So, higher friction means higher cohesion, that will increase the carding force, and also fiber to metal friction, fiber to pin friction, if it is high, then also carding force will increase. Flat top specification. So, flat top increase the wear point density. So, increasing the wear point density and height and the decreasing in wear point inclination result increasing in carding force. It is very important. So, what first let us discuss the increasing in wear point density. Suppose we have wear point 1, 2, 3, 4 wear points are there. Another case we are having closer wear point in within this zone. So, suppose this is a 1 centimeter, within this zone we have more number of wear point. So, fibers, suppose ideally the fibers are bending like this. So, more number of wear points per unit area here, and this is less number. So, you can see the when we are trying to pull the fiber in both the cases. So, this with the higher wear point density, it is actually coming in contact with more number of wear points. That means, the frictional force will be high and it will require higher force to get segregated. So, carding force increases with the increase in wear point density and height. Higher height means more penetration of fiber trapped within the carding zone, within the pins, and more penetration means more contact area, and it will have higher carding force, and also decrease in inclination. So, so it depends on the force, depend on the angle of inclination. So, that will see in the by derivation how the angle of inclination affect the carding. That means, the angle is very important for carding force, where we do not need higher carding force, like in case of synthetic fiber like polyester, the degree of inclination is high, and in case of cotton and other fiber where we need the to open up. So, we need higher carding force to open up fibers, cotton fiber we need higher carding force. So, we need the lower inclination, that we have seen by earlier derivations. Okay. For cotton, for wool we have seen, for cotton it is a less than 74 degree. Okay. So, carding index. So, carding index, what is carding? It indicates the level of carding. So, during carding we must understand, we must assess how much carding is has taken place. So, by the term carding index we actually we can evaluate, we can assess the level of carding. So, these are the pins, this carding, suppose cylinder pin, suppose cylinder pin, the side view, these are orientation. So, angle of orientation we can get here, and at the side view here. Now, carding index is NC W alpha by 100 H. So, what is the H is the height. So, NC is the cylinder speed. Cylinder speed, that means higher the cylinder speed, higher is the carding index. So, more carding will be there, okay. And H is the depth of the tooth. So, if tooth depth is more, that means carding index will be low, and W is the wear point density. Higher wear point density means the it is basically the carding index will be more, and alpha is the angle, carding angle. So, that this here is the carding angle alpha. So, at which angle the carding is taking place. So, that means it is directly proportional to the cylinder speed and wear point density and carding angle, and inversely proportional to the depth of the tooth. Okay. So, carding angle, carding index we can get from this, there is this example for a cylinder speed of 360 rpm with a 0.6 millimeter depth of tooth, okay. Tooth depth is 0.6 millimeter, and the carding angle is 17 degree. Where is the depth of tooth is H, here is the depth of tooth. The wear point density is 660 points per square inch. The carding index will be, if we see directly, it will be 67,320. So, that means it indicates of the level of carding. So, if we change this parameter, we will get, we can calculate the carding index for different combinations. Now, carding index we can see here, carding index indicates the level of carding, that means. So, you can see with this in x axis it is a carding index, the blue line indicates the naps per 1000 meter, and green line indicates the tenacity. So, carding, if we increase the carding, level of carding, the nap reduces, okay, gradually, and then it is becoming minimum, and tenacity of yarn increases, but it has got some optimum value. If we do over carding, that means nap will start increasing, okay, and the cylinder, that is the tenacity will drop. Now, let us see carding index equals C NCWA, okay, NCWA by 100 H. So, NCWA alpha by 100 H. Okay. Now, you can see this is the cylinder speed. If we increase the cylinder speed, that means the fiber will be initially opened properly, and what it will do, the nap will reduce, okay. Nap will reduce and tenacity of the yarn will increase. But if we keep on increasing it to a higher extent, in that case it will try to actually have higher load on cylinder and nap formation will be there. So, as the nap formation will be there, fibers are getting entangled. So, tenacity will also reduce. So, the optimum value is of carding index is this, where you have minimum nap and maximum tenacity. Now, coming to the flats. So, this is the flat configuration. This is one flat section, and this flat is actually, it is a width is 32 to 35 millimeter, the width of a flat, one flat, wear point 20 millimeter breadth, okay, and number of flats, total number of flats are typically 110 flats, okay, and the flats are connected by chains to form a endless belt, okay. And why it is chain? So, we need a flexible system, so that it follows the curvature of the cylinder. All flats are connected by chains and slide over flexible bend. There will be flexible bends will be there, and over that the chain slides. Together with the cylinder, the flat forms main carding zone. So, this is cylinder and flat. So, this total zone, this is called carding zone. In between cylinder and flat, that is the actual carding zone. Okay. So, this is the carding zone here, and in this zone the fibers are carded, as we have already discussed. This is, suppose this is the flat pins and here are the cylinder pins are there. So, together with the cylinder zone, flat actually flat makes the, this is the main carding zone. Here the following effects should be achieved. What are the effects? Opening the tufts into individual fibers. So, the fibers are in the tuft form and they will be opened to individual fibers with the help of the two sets of pins. Okay. Elimination of remaining impurities. So, impurity removal means when we are making it the tuft to individual form. So, that means the whatever foreign particles or impurities are entrapped within this tuft are getting exposed, and by the action of these pins they get eliminated. So, we need to eliminate some short fibers. The short fibers once comes into contact with the with the flat surface, they get embedded within the flat surface. So, they are not further, they are not coming into the carding zone again, because it penetrates inside the, because it is as a short fiber, these short fibers. So, I will just try to show you. Suppose this is the flat pins, okay, and here is the cylinder pin. Now, one short fiber, this is short fiber, during this action this so this is short fiber, another is the long fiber, this one is long fiber. Now, the short fiber which has penetrated inside the flat will remain in the flat, because it is not coming into the action of the cylinder due to its short length, and it will be carried away by the flat, and further it will be removed as a flat strip, flat waste. But the long fiber will have a chance to come back again and again with the action of cylinder. So, this long fiber will be carried away by the cylinder and will be ultimately presented to the doffer. So, untangling of nape is possible. So, you will see the napes are there, napes it will actually, if it is open, it can be opened. So, that will be unentangled by the this pair of wear points. So, that is also possible, and they can be eliminated. And if it is not opened, so opening is a first preference, that if it is open to a small long fiber, that is fine. If it is not open, then this naps will get again entangled with the flat surface, flat pins, and they will be removed subsequently. Okay, they will be eliminated from the total mass. So, the nape removal is also one important function of the carding, and also dust will get removed. So, these are the different factors, effects we achieve in the carding zone. Okay. And high degree of longitudinal orientation of fiber, that is also possible. So, here you will see this is the only process, first process, where the tuft multidirectional fibers, multidirectional orientation, tuft orientation, it gives a fiber with a almost longitudinal orientation, and that is possible in the carding zone. By this action, where a series of pins are, two series of pins are there, and they are moving at a different certain relative velocity, and the fibers are passed through this and get oriented. So, longitudinal orientation of fiber is also important here. So, in order to fulfill these requirements, a large continuous carding surface is required. So, this cannot happen in only one set of one smaller zone, only one surface, one flat surface. So, we need a series of long surface are required. So, that is actually provided by the series of flats. So, we require a continuous carding surface is needed, because repeated action is required to achieve this this function. Okay. The surface is created by large number of individual clothing strips secured by the bars and of the flats and arranged in succession. So, this continuous surface is created by a large number of flats, okay, large number of flats. So, it is a basically typically 110 flats are there, but within this zone it is typically around 40 flats are present in this zone. 40 to 46 such strips are commonly used to make the carding surface. So, this is the operational zone. Here you will see the 40 to 45 around the flat strips are present. So, that is very important. Even a single section, see, if we present only point wise section, point wise carding zone, this will not be sufficient. We need a series of carding zone, series of flats to make a continuous carding surface. Now, since the elimination of waste can be carried out only by filling the clothing, that means flat clothing, flat must be cleaned continuously. So, this flat actually moves, and all this waste short fibers naps are entangled. This is the flat, okay, flat pins are there. So, all these fibers are short fibers, naps are entangled. So, this must be cleaned. So, this cleaning is done by movement. Here flat has to come out, otherwise this total in the carding zone, if it is stationary, so this will be blocked. this after certain time this the flat wear points will be actually loaded with the short fibers, naps and all this waste material. So, then the performance of the carding performance will be deteriorated. So, we need to clean it continuously. So, they must therefore be moving. So, that is why this surface is not stationary. Okay. So, they must be moving just to clean the material. We need moving flat just to clean the material. Flat, if the flat is stationary, it will initially it will give the carding action exactly same as the normal carding action, but we need to clean it because the waste the short fiber, naps and other waste waste material like your impurities are embedded inside the flat wear points. So, that needs to be cleaned. So, that is why we need a revolving flat card. So, that is why we need a revolving mechanism which will move the flat. So, this card is also known as revolving flat card. So, although flat card and this is revolving, it is actually endless chain is there that actually moves. The bars of the flat must be joined together to form endless circulating belt, for which purpose they are fixed on a chain or toothed belt. So, they are actually fixed on a chain, okay, and they circulate continuously at very slow speed. Now, another arrangement is that between cylinder and this is a cylinder surface and it is a flat surface, it is called heel and toe arrangement. In our in our shoe we have the heel which is above the ground higher and toe is at the closer to ground. So, that arrangement it is there for each and every set. So, if there is a 40 the flat zones. So, in each set in each flat zone we will have the heel and toe arrangement. Now, I will just show this is one, this is first flat and cylinder, this is cylinder. So, you will have in this fashion, okay. This is second flat, third flat. So, this is heel and this is toe. So, back side it is a heel and front side it is toe. Why is it so? Because the fiber tuft when it is moving entering in the carding zone, it should penetrate smoothly and gradually the carding that compressive force should be higher. So, that the here compressive force, whatever compressive force is there, here the fibers are getting opened. So, you need to have maintain the compressive force. For that we have closer, relatively closer setting at the exit of each flat segment. So, this is the system here you can see this is one. So, in this section, so we can in this way this is a flat that heel and toe arrangement. Now, the movement here may be in opposite direction or may be in the same direction. They have got their technical implications that I will discuss. To facilitate a gradual increase in intensity of opening of the tuft. So, initially if it is higher distance. So, here the intensity will be lower. So, gradually as the fibers are getting opened. So, there will be gradual increase in the intensity of opening. So, and otherwise if it is just opposite. So, heel and toe. So, if it is toe and heel arrangement, then the things will be that suddenly the fibers will come with the lower setting, closer setting, and that will actually have that will try to, that will break the fiber, fiber will get damaged. Instead of opening, fiber will get unnecessary breakage of fiber will be there. So, out of 110 flats, so 40 to 40, around 50, 40 to 50 flats are in working position, but the carding action is completed within the first few flats, but the main carding action that I have mentioned, maybe 10 or 15 flats, the carding action is completed, that all fibers are there and remaining are there, the cleaning action. So, carding action is there. After that, the whatever the fibers are moving through the pins, they are actually having cleaning action and also to some extent parallelization, orientation of the fibers towards the axis. So, to remove the short fibers, why then flat moves? So, flat you can see here, now flat has to move, because as I have mentioned, the fibers are entangled, short fibers are entangled, naps are entangled with the on the flat surface. So, we have to move it to remove the short fibers from the flat. And also during the use, the flat gets flat wear points gets blunt. So, we need to have, so we need to sharpen by the grinding action, that is also possible, and we can grind the flat during its running position. When it is running, that time also the grinding can take place to match the curvature of the cylinder after grinding. So, that is why it is we need flat movement. Now, action of flats are there, you can see the flat location. So, carding force is maximum at the beginning. So, as the card, so it reduces up to say 50. So, after that the carding force becomes almost same, because carding force decreases linearly up to the 7th flat. So, here it is linearly increases, it is a sharp drop, sharp decrease is there and keeps decreasing up to 15th. So, it is 15th, it is decreasing, and then it is then flat, and then it remains constant. Typically it is like this. Okay. So, this type of effects are there. So, the remaining 25 to 30 flats are actually absorbing the minimum trash, okay, seat coats and naps, because initially the within 16th flat the main function is completed. Okay. As the flats move at a very slow speed compared to the cylinder in principle. So, it is moves we cannot move the flat at high speed. Okay. The flat can be moved either in forward direction or in backward direction, that is backward in the same direction or in the opposite direction to the cylinder. So, flat can move at the with the same direction and also with the opposite direction, because as compared to the cylinder surface speed, flat surface speed is negligible. Okay. But flat has to move, flat cannot be stationary because it has to move, because the we need to remove the fibers. Okay. Now, here I will just go back for now. Now, here now this is the cylinder, suppose cylinder is moving in this direction. The flat can move this direction, that means it is a forward moving, we can say, and where this flat, if it is moving, the cleaning can take place at this position, and then when it is coming back again, the clean surface at this side, it is a Licarin. Okay. Licarin. So, here you will see the clean surface is presented. Okay. So, it can move in both the directions. Now, let us see the forward direction. Forward movement, what happens? Forward movement means cylinder and flat, they move in the same direction. Now, let me draw cylinder, let me draw the flat in different color. This flat, they are moving in the same direction, okay, flat. And here what happened, you have the Licarin, this is Licarin, and here it is a doffer. So, when in the forward movement of flat, so the surface, cylinder surface and flat surface moves at the same direction. So, the advantage what we get, cylinder assists the movement of flat. So, with the cylinder direction, the flat we can get the drive from the flat, it assists the movement of the flat. Removal of flat strip is easier, because here the flat strips will be collected. The flat strip means the whatever waste particles are there, short fibers are there, and from here we can remove by the brush cleaner. So, that we remove from the flat surface, and we get the clean flat here, and it is presented in the at the initial zone, front zone. And the disadvantage is that the large size trash particles liberated at the first few flats. Now, suppose now here what is there now, suppose in from the Licarin along with the fiber, one large size trash particle is coming, and this large size trash particle liberates at the first few flats. So, here it will be liberated, it will be removed, okay, and flats, and affect further cleaning badly. So, what happened, it is gets and it the flat it is getting embedded with the flat. So, and what happened, if this large size particle is embedded at the initial stage, and this flat is travelling throughout this carding zone, throughout all this carding zone, and which is keeping on affecting the carding action badly, because this throughout this travel it is affecting the, because it is already loaded with the trash particles, its carding performance has dropped. So, cleaning action or carding action, they are affected throughout the entire carding zone. You can see the carding force is there and flat location. So, carding force is reduced. And now, what happens with the backward movement? So, forward movement has got their advantages, but main disadvantage is that it affects the cleaning action or affects the carding action badly. But what happened to the backward movement? Backward movement means when flat although moves slowly, but moves in the opposite direction. the relative motion does not matter, because its a flat speed is very slow as compared to, it is negligible as compared to the cylinder speed, but its movement affects, okay, it matters. Now, reverse movement against the cylinder brings some technological advantages as compared to the normal same forward movement, but most of the cards work on the forward movement. Okay. In this system, the flat comes into operative relationship with the cylinder clothing on the doffer side. Now, another advantage, let me tell you here in this another advantage is that when the flat material enters, the flat becomes clean. So, this will act, this helps the, you are presenting a clean flat. So, that will help the initial proper carding action. Okay. Now, backward movement. So, in this system, the flat comes into operative position in the, this is the, in this portion at the doffer zone. This is a doffer zone at the doffer side. So, it is the coming in the, so here the flat comes in the clean flat, but in this side when it is coming out, it is a fully loaded flat. At this stage, the flats are in the clean condition. So, this is the clean condition. So, what happens at the end, when the material is coming out. So, at that point we are getting the clean clean flat, that means the ultimate product will be better. Ultimate product, here the carding function will be very good. So, that will be, that will affect the, that improve the carding action. Okay. They then move towards the lacquering side, and gradually the fibers are getting filled up during the movement. So, so here it is a clean, then gradually it is filled up. Okay. And you can see that the flat loading, initially the flat load is very high, because it is due to the reverse movement. So, but at the end, towards the end of the carding zone, here this is 40th, suppose 40th one, here the load is very low, that means the proper carding action will take place here. So, improve cleaning action here. So, finally, the, if you see the quality or cleanliness of the sliver is improved in the backward movement of the card. So, part of this, part of the their receiving capacity is thus lost. Okay. So, here, but sufficiently remain to eliminate doubt, since this step takes place where the material first enters the flat. Now, so that means here in this zone, although they are loaded with the these flats are loaded with the impurities during this entire travel, but they have still some capacity, because initial portion the fibers are entangled more. So, there the gradual action is acceptable, but it will have whole carding zone. So, gradually the flat will be able to open up the fibers. At this position above the lacquering, so here above the lacquering, this is lacquering, the cylinder carries the material to be cleaned into the flat. Okay. So, here at this point, as I have mentioned, the material is actually although it is there in the loaded, but there will be still some cleaning action. The latter takes up the dart, but does not transport through the whole machine. So, here although it is taking the much more dart here, but it is not carrying the whole carding zone like your forward movement. Whatever large number of dart or higher dart content, it immediately comes out in this side. So, that is why it does not affect the remaining carding action. Here carding action is we are getting proper carding action. So, initially whatever loading and here initial dart particle is coming from the Licarin, so that gets immediately removed. So, that is the main advantage of this forward system. Okay. So, that whole machine, as in case of the forward system, it is a backward system, that is the main advantage. Forward system, this dart particle moves along with the flat throughout the carding zone. Instead, the dart is immediately removed from the machine directly at the point where flat leaves the machine. So, here the material comes, the dart, whatever the trace particle comes here, during the action it gets embedded with the flat at this point, and large. So, this is the Licarin. So, fibers with a large particle is coming. So, it gets embedded with the flat and immediately it is getting out. Okay. So, it is cleaned, okay, as the flat at this point. Now, coming to the what we have discussed, the flat and cylinder region. Now, we will discuss the flat and doffer region. So, here we have three typical plates: percent plate and door is there, and bottom plate. So, percent plate is the top plate and door, which is actually to use the it is used to inspect the cylinder clothing, whether it is all right or not, and grinding of the cylinder. So, that is used, and bottom plate is another plate here. The main purpose of this covers to keep the fibers on the cylinder surface. So, if you see here that cylinder, flat, cylinder is moving, and here you have doffer. So, when as soon as it is coming out of the flat zone, fiber is coming out of the flat zone, there the tendency is that here cylinder, flat zone, it is moving, and here this is a doffer. Now, what we are discussing, this is the zone flat and doffer zone. Flat and doffer zone is this. Now, as soon as the fibers are coming out, here due to centrifugal force, fiber is always tends to come out from this. Before it reaches the doffer, due to centrifugal force, fibers may come out. So, here we need plates covers. So, there are these plates are of three types of three segments. So, three plates are the top plate is known as the percentage plate, and middle plate where we need a grinding of the cylinder surface, and there is a bottom plate. So, main purpose of these plates are it's so that the fibers remain on the cylinder surface to actually to prevent the fibers from coming out due to the air current and centrifugal force. There will be some air large air current, air vortex created at this zone. If we do not use these plates, so the fibers will be thrown out of the cylinder surface. Okay. It will not before it goes to the doffer. So, top plate, you can see this is the top plate, front top plate, and the flat is coming, flat zone is ended here, it is going out, now cylinder. Now, here you can see at zone A the air current is created. Okay. If the plate is closer to the cylinder, so this is zone, this is a plate, here you can see this is the plate here, this is a front plate. Now, two positions are there, this is closer, this one is little bit away, and the bridging fibers, what is the bridging fiber? The fibers which are in contact with the both in the flat and with the cylinder, that is the bridging fiber. While the flat is leaving the carding zone, at that point there will be few fibers which are in connection with its contact with both the cylinder wear point and the flat wear point. So, these are called bridging fibers. So, if the plate is closer to the cylinder, so here it is closer to the cylinder, the chances of fiber moving along with the cylinder is more. That means, if it is closer, that means one is the that air current will be higher air current, less air current will be created, and also if it is closer there will be opening, okay, opening, the air will the suction, through the suction vacuum here, due to the movement the air will be will enter here. If the top edge of the plate is closer to the cylinder, so that which means lower alpha. So, this is closer to the cylinder, the alpha will be lower. So, if the alpha is lower, that means P or cos alpha will be high, P cos alpha is high. So, then the velocity of air A is increased. So, when it is lower, that means opening will be high. So, velocity of air is increased, causing more bridging fiber to go to the cylinder. So, this bridging fibers are there due to the lower angle. So, P cos alpha will be high, that means the force towards the with the cylinder clothing is high. So, bridging fiber will be actually will be pulled away from the flat. So, it will go towards the cylinder surface. So, the fiber loss will be less, okay, and air velocity is increasing also here. So, air velocity increasing means the fiber will be pushed towards the cylinder surface from the flat surface. So, both this function comes into picture, which helps in reducing the fiber loss, and bridging fibers are typically long fibers. So, long fiber loss will be there. So, setting is extremely important here. Now, the another part is which is called fiber shedding. What is fiber shedding? Fiber shedding means the removal of fiber from one surface to another surface. Here fiber shedding we are telling, this is the doffer angle. So, you can see for fiber shedding, fiber removal from the from one surface, fiber shedding. So, it requires different forces. One force is that it is a centrifugal force. Centrifugal force is acting radially upward. So, higher centrifugal, suppose there is a fiber, here. So, higher centrifugal force means higher chances of fiber coming out from the surface. like from cylinder surface, if the cylinder surface to doffer surface, fiber has to move. So, cylinder surface has to shade the fiber, cylinder surface actually will be actually transferring the fiber from the cylinder surface to the doffer surface. So, there is a centrifugal force, higher centrifugal force means higher chances of fiber shedding, and air drag acting parallel to the clothing. So, the P is the air drag. Now, air drag actually tries to that fiber tries to retain the fiber within the that surface, that is cylinder surface. If we talk about the cylinder surface, air drag is actually tries to push the fiber with against the cylinder clothing. So, that will actually, so it will this is higher air drag means lower chances of fiber shedding. So, T by P is the function which actually is, if it is high, then higher chances of fiber shedding will be there. So, we will try to measure the T by P ratio. Now, here mu beta is the inclination of wear. So, you can see here. So, this beta is the inclination of wear point, this is the inclination, and here, and if we resolve the T value, T is the centrifugal force. So, T is actually, you can resolve it, one is the Q, another is H. So, Q is equal to T sin beta. So, T sin beta, and H is the this H force, H is T cos beta. So, these two forces we are actually now resolving P here, P has got two components Q and H, capital Q and H. So, Q is P cos beta, okay. The P has got two components P cos beta and H is P sin beta. So, these are the two forces, one is for centrifugal force, another is for the air drag. So, two forces are being resolved, two components. Now, what we are getting here, you can see normal force gives rise to the frictional resistance. So, this normal force, whatever normal force is there, it gives rise to the frictional resistance of the fiber movement. So, it resists the fiber actually shredding. Now, if you see F is the normal force. So, F is the normal force which is equal to mu into the norm, F is the frictional force, frictional force equal to mu in multiplied by normal force H plus H. So, these two forces are in the same direction. So, this is the frictional force which resists the fiber shedding. Now, in the equilibrium equation is that, so N equal to, the N is the force in the other direction. So, H plus H. So, this H plus capital H plus small h equal to P sin beta plus T cos beta, and whether Q here, Q is small q is that is equal to F plus Q. F, what is F? Now, you can see we know that the F is nothing but mu n, n is the normal force and the mu is there, that frictional force. So, T q is small q is T sin beta and capital Q is P cos beta and F is nothing but mu multiplied by N, that is the frictional force. Now, you can see here this F, we can actually replace this F here. So, this N with this equation. So, ultimately the equation becomes T sin beta equal to P cos beta plus mu, and N is replaced by P sin beta plus T cos beta. So, and rearranging this equation, what we get? So, fiber can move towards the tip of wear point if Q, this Q force is more than Q plus Q. If it is there, then the fiber will move out of the, it will be threaded towards the, from the cylinder surface to the doffer surface, if small q is more than this Q plus F. So, what does it mean? Small q is actually, this is the T sin beta, okay. The small q is T sin beta, more than Q is the P cos beta, and F we have already derived this F. So, this is the condition for the fiber to move out of the, for a shading, move out of the wear point. So, if we just rearrange this equation, T by P equal to more than cos beta plus mu sin beta divided by sin beta minus mu cos beta. So, this is the relationship for the fiber shading. Okay. That means, higher T means higher fiber shading, so centrifugal force is given by, this is the centrifugal force m v square, v c square by r, and m is nothing but fiber, if we know the fiber density, fiber length, diameter of fiber. So, pi d square by 4, and total length of fiber is L, rho is the, rho f is the fiber density. So, this is the fiber mass, and the centrifugal force is T. So, mass of fiber m, and v is the velocity of the cylinder, r is the radius of the cylinder over the tip, that is the, at this point over the, this at this point the radius. So, here is the total centrifugal force which actually helps in fiber to move out of the cylinder. D is the fiber diameter, and L is the fiber length, rho is the fiber density. From this equation we can calculate the centrifugal force. Okay. Now, centrifugal force is T m v square, m v c square by r. So, substituting m in T. So, it will become, T is becoming this. So, here we are substituting m here. So, this m is substituted. So, the centrifugal force m becomes pi d square, L fiber length, rho f is the fiber density, V c is the cylinder speed, r is the radius of cylinder. Okay. So, that we can get, an air drag force P is given by this half C A rho a square and V relative square. So, what is that? V relative velocity is the, that cylinder speed minus the air speed at certain distance. Okay. That is a relative velocity, and C is the coefficient of air drag, rho is the density of air, and A is the largest projected cross sectional area. So, we can get the air drag force which works against the fiber shading. So, if we can calculate the T by P ratio, so relative velocity is 0 if the fibers are closer to the cylinder surface, and it is actually increases, and it will be equal to Vc, it moves further away from, so that in that case the that air movement will be 0, that we have discussed. Okay. So, the relative velocity is from the that is the velocity of cylinder and the velocity of air. Therefore, T by P we can get from the earlier derivation. So, this is the T by P, and the higher this value, higher the T by P value, that means higher will be the fiber shedding, chances of fiber shedding. So, the chances of fiber shedding being thrown off the wear point, it increases with the increase in the numerator value. What are the numerator value? So, with the increase in cylinder speed, the cylinder speed, diameter of the diameter, and density of fiber. So, diameter of fiber and density of fiber. So, these are the parameters. So, if we have coarser fiber, so fiber shedding will be easier. If we have denser fiber, fiber shedding will be easier. If we have higher cylinder speed, fiber shedding will be easier. But it is with the decrease in cylinder radius. So, cylinder radius if it decreases, so that means it will increase, that if it is so higher cylinder radius will reduce the this fiber shedding. So, for to have the better fiber removal from the cylinder surface, we need lower cylinder radius and relative air velocity. So, relative air velocity should be low, should be actually should be low to have higher fiber shedding. I think we have discussed the basic theories of carding and fiber shedding. So, we will stop here, we will take up the another topic in the next session. Till then, thank you.